Hello friends, this is Prof B Oza. We will be talking on ground relays today. In last tutorial, we talked about two kinds of relays in overcurrent protection. One is the phase overcurrent relay and second is the ground relays. So we were talking that the setting philosophy, relay setting philosophy for both kinds of relays are different. So let us talk as to what is the relay setting philosophy for ground relays. How can we decide the settings, relay settings, plug setting, time multiplier setting, and other settings of ground relays. As we have talked in last tutorial also, someday we will be talking about how to configure the numerical relay for phase versions, ground versions, etc. But we have to start slowly. So we have talked about phase over current relay, now the ground relays. Meaning of ground relays. The ground relay means they sense the ground faults only. That is the ground relay. Sense the ground fault means the faults that involve ground. That is either LG or double line to ground. That is single line to ground or double line to ground. Triple line, double line faults are taken care of by phase over current relays, about which we have talked, and we have also calculated one numerical for finding out the plug setting and time multiplier setting, even setting of high set unit for phase relays that we have done. So now the ground relays. So what are the considerations for setting ground relays? The very first consideration is the ground relay shall not operate for triple line or double line fault. Right? Because whenever triple line or double line fault occurs, and if it is a sustained fault, then the line staff, the patrolling staff has to patrol the whole line, has to go through, has to pass through the line, has to. Usually the transmission lines are parallel to the highways, so they will travel on highways at a slow speed. In earlier days, they had to travel at a so slow speed because the location of fault was not known. Now the numerical relays suggest exact location also, so you can reach there fast. But then after reaching there, for which kind of fault you are trying to, which kind of fault you are, rather, which kind of fault you are sensing, or which kind of fault the relay sensed and which kind of fault you have to look for. You see, LG fault occurs in a different way, double line fault occurs in a different way, so it becomes faster if the line staff knows that it is really an LG fault. LG fault means it will be across the flashover. I mean, it will be flashover across the insulator. Then that insulator would have burnt, or it would have become black or something. So you see, one has to know. So for knowing, it is, and that is very important function of protective relaying system, that it is to let you know the kind of fault also, not only the distance to fault, but the kind of fault also. So first thing, it must not operate for triple line and double line. That is first consideration. So how do we do that? So for doing that, the ground relay is connected in residual circuit of 3 line CTs. Residual circuit of 3 line cities. What is that connection? That connection is this. That connection is this. Residual circuit. There are 3 line cities, and the residual connection is 51R, 51Y, 51B. That all are phase relays. So that we have talked about, right? 51R means it is phase overcurrent relay, usually normal inverse IDMT overcurrent relay. 64 is a number for ground overcurrent relay. These numbers are NC numbers. These numbers are internationally known. If you write 64, everybody throughout the world will understand that you are talking about ground overcurrent relay. So we are talking about 64 now. It is connected like this. No doubt, if you have a numerical relay, you have not to connect the relay exactly like this, because you see, in that case, you have got only 3 line CTs and you have the secondary GUCs, IR, IY, IB available. You have to make sum total, and that sum total IR plus IY plus IB is to be fed to the ground relay. That summing up can be done by numerical relay, because after all, numerical relay is also a computer. It's a processor, so it can calculate the current and can feed that calculated sum IR plus IY plus IB to ground relay. But in earlier days, for electromagnetic and static relay, we were connecting CTs like this as shown, right? So IR plus IY plus IB is passing through 64. And because IR plus IY plus IB is passing, and as we know that under very normal condition, normal means no fault, no kind of fault, normal current passing through transmission line, normal current IR plus IY plus IB is always 0. Sum total of 3 phase current in a balanced system is always 0, and therefore no current passes through 64 usually, and therefore the setting philosophy does not demand for flux setting to be higher than normal rated current. In phase over current relay, our flux setting, say of 51, 50R, 50Y, 51R, 51Y and 51B has to be more than normal rated current. Here, for 64, that is not the consideration. Right. Then what is the consideration? The consideration is possible mismatch. The consideration is possible mismatch between the 3 line CTs. When triple line fault occurs, say for example, these are 100 bar 1 CTs, triple line fault is 1000 ampere, then 100 has to be reproduced as 1, 1000 must be reproduced as 10, but unfortunately 1000 is not reproduced as 10 because CTs saturate. And once again, unfortunately, all the 3 CTs do not saturate by same amount. There will be mismatch. There will be non-identicity between saturation characteristic of 3 CTs, and therefore some spill current will flow through 64. The relay should not operate for that spill current, and therefore you have to safely decide. You have to you have to be very particular while deciding the sensitivity of a relay, right? That means the plug setting of a relay. That is the requirement. Right? Now you can see that if the cities do not saturate, then IRF plus IYF plus IBF, that is the sum total of 3 currents when triple line to ground fault occurs, then also it is usually 0. So relay does not operate and should not operate. For double line fault, if you see double line fault, and when we talk about faults, we ignore pre-fault currents, because pre-fault currents are usually very small with reference to pre-fault currents are very small with reference to normal, with reference to the fault currents. Fault currents are usually 10 times the rated current, 5 times the rated current. So we do not consider pre-fault currents. If we do not consider pre-fault current, then from IB fault, IY is equal to minus IB, right? You can see I have written IY is equal to minus IB and IR equal to 0 because there is no fault in our phase. So IR plus IY plus IB, if you make, then once again it is 0, and therefore no current through ground relay, and relay does not operate and should not operate also. So relay will operate only if LG fault is there, single line to ground or double line to ground. For no other faults, the relay will operate. So that is our requirement, and that requirement is fulfilled by such a connection. That is relay, ground relay being connected in residual circuit of 3-line series. That is the first thing. Second thing is, if you want higher sensitivity, if you want better sensitivity, then also there are ways and means. You can connect the relay in a different way. The ground relay can be connected in a different way. Then if you connect the relay in a different way, then you can get the higher sensitivity. Say for example, this one of the ways in which you can connect the ground relay is this, right? That is, I have got secondary of a transformer, right, which is star connected, and ground point is available to me. So that is very necessary that neutral point has to be available on terminal plate. So you can connect between neutral and ground, you can connect a city which is known as neutral city, and as shown across the neutral city, across the secondary of a neutral city, you can connect the ground relay, which you can see will sense only ground faults. Because if triple line fault occurs, current is not going to pass through neutral. If double line fault occurs, current is not going to pass through neutral. The current will pass only for an LG or double line to ground fault, and then only 64 will sense. And here it can be more sensitive because there is no problem of mismatch between three cities, because there is only single city now. That is the reason why you can make the relay more sensitive. But obviously, the neutral point in power system has to be available for such a connection. The other way, the second way, is you can connect a relay across CBCT, core balance city. The core of a core balance city encircles, encompasses all three phases, right? So flux will be produced in the core only when the sum total of current IR plus IY plus IB is not zero. So IR plus IY plus IB is always zero under normal condition. IR plus IY plus IB is always zero under three-phase fault. IR plus IY plus IB is also zero under double line fault. So only for line to ground fault, that means zero sequence current is present only for line to ground or double line to ground. Then the flux will be there in the core. That flux will cut the secondary winding, and there will be an operating juice for relay 64. Right. So this is, once again, there is only single core, no mismatch between three city cores. Therefore, you can make the relay more sensitive, right? But the problem is you can have CBCT only with cables, not with overhead transmission line. Because for 66 kV transmission line also, the distance between R and Y and B phases is some 1.5 to 2 meters. Right. So if it is horizontal configuration between R and B, it will be some 3 meters, and you have to have a core. The core diameter should be more than 3 meters. This I am talking for 66 kV line. If I talk of 220 kV or 400 kV line, the diameter has to be more than 10 meters. You see, this is just not technically feasible. You cannot have a core diameter of such a large, you cannot have a core of diameter of such large dimension. Therefore, and if at all you do it, then there will be heavy leakage fluxes and there will be no operating juice available for 64. Cables are three, RYB are very near to each other. So you see 66 kV cables are available. So when 66 kV line is through cable, you can have a CBCT, or otherwise usually 11 kV and 6.6 kV are always indoor. They're always cables. Therefore, CBCT is usually used for 11 kV and 6.6 kV systems. So that one has to remember. So these two connections, you can increase the sensitivity. Monitoring the ground relay by under voltage relay is usually not required because under voltage relay or voltage controlled overcurrent relay is required when ZS by ZL is high or the fault current is less than the normal load current, which is not the case. ZS by ZL will never be high in case of ground relay because ZL itself is very high. Because ZL is high as ZL incorporates zero sequence impedance, and zero sequence impedance is very high, usually 4 times positive sequence impedance for EHV long lines. So that is not a problem. So ground relays are usually not having the voltage controlled feature, or rather voltage controlled overcurrent relays need not be used, and the fault current is purely dependent on distance to fault. It has nothing to do with, or rather it has to do very less. It is very less affected by the source impedance. Therefore, this is done. So these are the two ways in which you can connect. Now the third thing, the third important thing. Third important thing is this, that LG fault, the formula is this. E, that is phase to neutral voltage, right? Upon Z1 plus Z2 plus Z0 plus 3Zn plus 3Zf. Z1, obviously, everyone knows it is positive sequence impedance of the power system. Z2, negative phase sequence impedance. Z0, zero sequence impedance. Zn, if at all you have connected deliberate impedance in the neutral circuit, that is the value. Zn and Zf is the fault resistance. It is usually resistive because it is flashover. So flashover arc resistance is usually resistive. So Zf is resistive. Now, even if you have not connected in any Zn, because usually for EHV lines are solidly grounded. Zn is 0. So, but even in that case, Zf is very high in case of ground faults, which is very low in case of double line fault, hardly 2 to 4 ohms. But for single line to ground fault, its value can be 20 ohms or even 50 ohms are found in field when your lines are erected, they are installed in hilly areas, in the areas where asphalt surfaces are there. There, the soil resistivity is very high. And what is RF or ZF? RF is resistance of flashover path, which may be just 4 ohms, but plus resistance of iron tower, which would be quite high because iron is not a material having good conductivity. Right? So iron tower resistance is quite high. Current is going to pass through iron tower. And tower footing resistance means soil resistance. And soil resistance is variable from place to place. Therefore, and in the formula you see it is 3ZF. Also, Z1 is equal to Z2 for transmission line and Z0 is roughly 4 times Z1. So if you see, denominator becomes quite high and the fault current can be very low. Fault current for single line to ground fault can be very low. In many cases, it can be lower than, the uh, normal rated current of transmission line. So it is difficult to sense. So how it is sensed? It is sensed in this way, that the sensitivity range of ground relays is different. It was 50 to 200% for phase overcurrent relays. For ground relays, the sensitivity range is 5 to 20% as shown, right? 10 to 40% or 20 to 80%. Three ranges were available in earlier days. But if you use numerical relay, they give very wide range, say 5 to 100% or 5 to 200%, because it is quite possible in numerical relays. Also, in our electromechanical relays, 5 to 20%, only 7 steps were possible. That is 5, 7.5, 10, 12.5, 15, 17.5 and 20. Only these 7 steps were possible. Whereas here in numerical relay, it is not like that. You see, in steps of 0.1 or even in steps of 0.05, you can vary the setting. So steps are also closer. More number of steps are available in case of the numerical relays. So numerical relays that way are better. They are more, so to say, uh, more accurate and more, you have wide ranges possible. So that is the advantage of numerical relay. So that is the very important thing, that the sensitivity range, the flux setting range of the ground relays is different. The next thing is the presence of delta Y transformer. Next thing is presence of delta Y transformer. Now what happens, you see, you can see that I have got a system like this, which we have been talking, right? I have simplified the system. System is not this simple. I've got a generator transformer, and then bus A, some transmission line AB, then another transmission line BC. It is not necessary that from A only one transmission line is going. There will be some 10 transmission line emanating, right? But generally, if I want to simplify, I can draw a drawing like this. But at bus B, immediately the transmission line does not start. We step down the voltage. Say GT is 15.75 to 220 kV. Then at B, we step it down from 220 kV to 132 kV. At C, we step it down from 132 to 66. At D, we step it down from 66 to 11. Like that, we go on stepping down. Usually, it's not so that there are no switching substations. There are certain places. Say at Gondal, Western Gujarat region, Gondal, 220 kV substation. There is a switching lines also. That means 220 kV lines comes. The incoming line is also 220 kV. Outgoing line is also 220 kV. Then two relays, say R1 and R2. I was telling to you that R1 and R2 is not single relay. R1 are 4 relays, as we have seen. 3 overcurrent relays, phase overcurrent relay, and 1 ground relay. So ground relay R1 and R2 will become dependent to each other. You have to coordinate R1 with R2, or so to say, you have to coordinate R2 with R3 only if there is no delta Y transformer. But usually the delta Y transformer is present, and when delta Y transformer is present, the problem comes. What kind of problem comes? Say there is a BG fault. So BG fault, you can see that when we ignore pre-fault current, so IR and IY are 0. IB is IF, fault current IF. That reflects in primary phase winding. But if you see in primary line windings, IF in B, but that same IF is going like this, and in R phase also there is IF. So the line to ground fault in star side of a transformer is seen as double line fault on delta side. And usually in power system, our transformers are delta Y, because we would want to suppress the harmonics. Therefore, transformers are usually delta Y. YY are very rarely used. Therefore, the line to ground fault is seen as double line fault, and double line fault cannot be sensed by ground relay. So, fault on, say fault on line CD, if there is a ground fault, that is not at all sensed by R2. So now R2 is not to be coordinated with R3. And when I say that R2 is not to be coordinated with R3, means the flux setting of ground relay R2 should be higher than 1.3 divided by 1.05 of flux setting of R3. That formula which we were using in phase overcurrent relays is to be used only if there is no transformer, if there is no delta Y power transformer intervening between two relays R2 and R3. If a delta Y transformer intervenes, then this formula does not hold good. That means R2 is purely independent of R3. R2 is not to be coordinated with R3. Flux setting of R2 can be independently set. This is very important. Similarly, We were talking. What we are talking for phase over current relay, that R2 should reach up to D and R1 should reach up to C. That is, phase relay R2 should reach for double line fault at D with minimum generation. All these what we were talking about in phase relays. Now that is not true because ground relays, for ground relays, because R2 does not reach to D. At C there is a transformer, there is a delta Y transformer. So question of R2 reaching to D does not arise. Question of R1 reaching to C does not arise if there is a delta Y transformer. Another important thing, time of operation of R2 should be equal to time of operation of R3 plus that discrimination margin 0.25. No doubt I was telling to you that with numerical relays you can reduce the discrimination margin to just 40 milliseconds. But usually, if you forget about numerical relays now, we keep it to 50 millisecond. So that 250 millisecond of discrimination margin comes into picture only if R2 and R3 are to be coordinated. When they are not required to be coordinated, there is no time discrimination margin between R2 and R3. TMS of R3 and R2 are independent. R2 can operate even faster than R3. If you want, R2 can operate even instantaneously. So the conditions for setting of the ground over current relays are quite different. They are altogether different. That one has to keep in mind, right? Ground relays philosophy, as I was telling, is quite different. Now the next thing, next very important thing, and the last thing is the excitation current of CT, right? So what we were telling in phase over current relay, that I have got 100 bar 1 CT and my current flowing in transmission line is 90 ampere. So 100 bar 1 for 90 ampere in secondary becomes 0.9 ampere and 50 to 200% in 7 equal steps. So 50, 75, 100 were available. So I was setting the relay at 100%, that means 1 ampere. And 1 ampere means what I was telling? I was telling that 1 ampere in secondary means 100 ampere in primary. That statement was wrong. But I used that statement that 1 ampere in secondary is 100 ampere in primary. Other way telling 100 ampere in primary is 1 ampere in secondary. That is wrong because there is an excitation current of CT. If I take one typical excitation current 50 milliamperes, that is 0.05 ampere, then 100 is reproduced as 1. But out of that 0.05 is taken by the excitation circuit and available to the relay to load is only 0.95. So 100 is reproduced as 0.95. Or other way around, if I want to tell, 1 ampere in secondary does not mean 100 ampere in primary, but it means more or less, roughly 105 ampere in primary. So 105 ampere is reproduced as 1 and not 100 as 1. So not 100 but 105 means there is a 5% error. So in my statement or in my calculation, there was 5% error, which I ignored in case of phase relays. In case of ground relay, now I cannot ignore that. I cannot ignore that because my relay is connected in residual circuit of 3-line CTs. I'll bring that slide again. This connection, my friends, it is connected in residual circuit of 3-line CTs. So what happens is that 51R, 51Y, and 51B are there. So if there is line to ground fault, B to G fault, then that B phase fault current will come to secondary, and out of that secondary, that current has to feed the excitation current of all the 3-line CTs because they are parallel now. So that current which is coming out, secondary juice, has to feed the excitation current of 3-line CTs, and then remnant current will pass through 64. So my friends, if I have set 64 at 10%, 10% of say 1 ampere, because my CTs are 100 bar 1. So 10% of 1 ampere is 0.1 ampere. So my plug setting becomes 0.1 ampere. So I take it for granted that when the current exceeds 0.1 ampere, the relay will operate. That is true. There is no wrong. There is nothing wrong about it. But that does not mean that 100 ampere primary is there. So in primary, if it exceeds 10 ampere, relay will operate. That statement is wrong. Because for 64, I need 0.1 ampere. But for each of the three CTs, I need 0.05. So 0.05 plus 0.05 plus 0.05, I need 0.15 amperes. 0.1 ampere for relay, 0.15 for three CTs. So it becomes 0.25. And for 100 bar 1, if 0.25 is primary current, secondary current, 0.25 is secondary current, then primary current becomes 25 ampere. That is 10% sensitivity of 64 means 25 ampere in primary. 25 of 100 becomes 25%. So when I say relay is sensitive by 10%, it is not really sensitive by 10%, but it is sensitive by 25%. So my real sensitivity when I say is 25%. So I have tabularized for different plug settings. Say if I say 5%, 5% means 0.05. You can see the table. X, first thing, 0.05 ampere is my sensitivity for relay. I have to add 0.15 to that because 3-line CT requirement is, yes, good. If I have got better series, the excitation current is 0.03 ampere, then 0.15 will become 0.09. I do agree. I've got better and better CTs are available in power system nowadays, but this is one calculation. So 0.05 plus 0.15 becomes 0.2. I need 0.2 ampere of juice and 0.2, right? 0.2 is 20 ampere for primary if 100 bar 1 CT is used, and 20 ampere is 20%. And if I calculate the error, what is the error? My sensitivity, I talked of 5%, but it is really 20%. So 20 minus 5 upon 5 into 100. So 20 minus 5 is 15. 15 upon 5 into 100 means 300. So my error in calculation is 300%. In phase relays, it was 5%. Here it is 300. I just cannot ignore this. So your calculations cannot be done in primary terms. You will have to come to secondary. You will have to consider the excitation current while calculating the plug setting, time multiplier setting, etc. Not only that, but you must one must appreciate that 5% sensitivity is really not 5%, it is 20%. So going to very sensitive setting is not much useful. You go to very sensitive settings only if you feel that it is a dead requirement. You are really requiring that. Otherwise, you don't go for that. Forget about that sensitivity, right? I mean, there is no use. Because if you see in this table, 80% sensitivity, 0.8 ampere offsetting gives me 18.75% error. So error is reduced. So it is better to go for lower sensitivity than for higher sensitivity. That means it is better to go for 80% rather than 5%. That is what is suggested from this table. So this is very important in ground relays and one must take care of this, right? So the error, as I told to you, is calculated from table, column P, column Q, that is P minus Q upon Q into 100. That's how we have calculated an error. No doubt, if you have got the connections of the relay in neutral circuit or by CBCT, then there is only one core and our multiplier, that is 0.05 plus 0.05 plus 0.05 is gone because now only 1.05 is required. Therefore, in this table, we are multiplying 0.05 into 3. This multiple 3 will go away and that multiple will be only 1. So the sensitivity, overall sensitivity, if the other two kinds of connections, that is connecting the ground relay neutral circuit of the uh, uh, in the secondary circuit of the neutral CT, that would give me better sensitivity. If I use CBCT, that would also give me better sensitivity in primary terms also, right? So that is the advantage of those two connections. But that I told you that CBCT can be only used for 6.6 and 11 kV, and the neutral connection can be used only if neutral is really available in your substation, in your system. Then you can have that connection. So these many things are to be kept in mind, my dear friends. These many things you must keep in mind. All these things, no doubt we'll be calculating one numerical on how to find out the settings in case of ground relays. We'll do one numerical. But if you want to do more numericals, if you want to do practice, if you want to get yourself examined, assessed as to how much you know power system protection, right? Whether you have really known it, this is I am lecturing, but you have to know. One has to know. The other person has to know. So for that you have to be assessed, you have to be analyzed, your logical power, your thinking power, your analytical ability, all these things are measured by the app AdaptMe. And on AdaptMe, we have already loaded 3 courses of mine on of power system protection. So you have to go to those courses and subscribe for those courses. Till then, please remain with AdaptMe. I'll be keep on uh, discussing. I'll be keeping on delivering different topics on power system protection. Our next topic is the calculation of relay settings for ground relays. Then we are going to complicate the system. We will calculate the plug setting and time multiplier setting for parallel feeders, where the directional feature will come into picture, right? Then we can go further and we can find out the plug setting and time multiplier setting of relays, coordinate different relays in an interconnected system. We may take a simple interconnected power system and do the calculations. So that way we will be covering the total overcurrent and earth fault protection in this short tutorials. Thank you till then, my friends. Have a good day.